everybody. This is the second segment of the Mesozoic. And I stopped at the Cretaceous where the sea level is higher than today, about 200 meters higher. And these are the possible causes of that high sea level. The first one could be that there was very active tectonic activity. The tectonic activity was at very high levels since Pangea has been breaking up. And so it's reducing the capacity of the shallow ocean basins. The other one is the lack of polar ice because of the warmer climate. So when there is no polar ice or glaciers, then the sea level of course goes higher. And the other one is the thermal expansion. Like when the water is warmer, it's actually expanded, just like our body, you know, like in the summer you cannot take off your rings because it's actually kind of swollen from the heat. So it's the same with the water. So it could be that a lot of the oceanic water spilled out of the ocean basin and flooded the continents. So therefore it was a Pyrrhic Sea at this time. So now let's look at how did the breaking up of Pangea happen. So start with the late Triassic. That's when Pangea have started to break up. And that is the first stage of the breaking up. And it started with rifting between Laurasia and Gondwana. So it was right here. You see this area right here, or right here, and that is when the Gulf of Mexico gets established. And the second one is the rifting of North America from Africa. So right here is Africa and North America. And as I said, the Gulf of Mexico formed during this time, right here, so right here. And because the Gulf of Mexico, as it formed, it was surrounded by land on every single side. It was a landlocked basin. So it was very, very dry there. Therefore, lots of evaporite formed. Remember, evaporite is salt, gypsum, and hydride. These guys are the evaporite. So a lot of those have formed during this time. So this shows you the early Triassic. Pangea is all together. This is the Tethys, the Panthalassa, and Pangea. Of course, as Pangea formed, there was a whole lot of mountain ranges, lots of it, which also caused a very, very, very dry climate during this time. And this shows you the second phase of the breaking up. The different Gondwana lands have started to actually rift away from each other, and this is the time when India is breaking apart and starts moving up north to, as you know, right now is colliding with Asia, making the Himalaya mountains right here. So this is the time when India started to move up north. This here shows you the middle Cretaceous. And as you can see, India is completely broken off and started its journey up north. The Atlantic, the northern and the southern Atlantic got established. The Tethys Ocean is starting to close up. Yeah, so basically during the middle Cretaceous, things start to look like they are today. And this here shows you the late Cretaceous. And India moved more up, Tethys Ocean closing even more. The Gulf of Mexico has actually been established, and as you can see, the Atlantic Ocean started to look like it is today. And this here is the latest Cretaceous, and that just basically shows you the end of the Cretaceous and how did it look like at the time. As you can see, the Mediterranean is pretty established. Tethys Ocean almost completely got closed in. And one important thing, that Australia and Antarctica actually have separated, and that just means that that this is moving this way and Antarctica is moving toward the south because the ocean is forming right here. So that is what's setting everything up to the ice age we are in today. Okay, so we're not continuing anything now as we did during the Paleozoic. by the sequences. We're actually gonna go region by region during this time. So we're gonna start with the Eastern North America, and this is where actually Pangea started to break up, right in the eastern part of North America. And as you know that during the early and middle Triassic, from the Appalachian, the sediment actually started to weather away and filled up like intra-mountain basins, like, which means basins between the mountains. And this is the area where actually the rifting started, the rifting which formed the Atlantic Ocean. So the very first Mesozoic rift basin formed right in the eastern part of the United States. The erosion of the Appalachian Mountains actually completely got finished by the end of the Cretaceous, like the end of the Mesozoic. That just means that there was no Appalachian anymore. It was completely flat, and the streams were meandering when there is absolutely no gradient. So it was a flat area, and this is the time, as I told you. So that was by the Cretaceous. But now if we go back to the Triassic, that's when actually the rift basin started to form, as I already kind of mentioned it. And when the rift basins were there, the sediment from the Appalachian went right into the rift basins. And we do know that the Appalachian must have been really, really tall, because if you drill into these rift basins, they contain about 6,000 meters of immature, coarse-grained detrital sediment which accumulated in them. So 6,000 meters, that just tells you that the Appalachian had to be at least 6,000 meters high. You know, that's 6 kilometers, that means more than 4 miles. And I bet this basin have lost some sediment because it might have not gotten in them. So the Appalachian was about as high as the Himalaya today. So if you look at this, was the breaking up of the Pangea. The red ones are the rift basins, and this is the Gulf of Mexico area right here. I have a better one right here, which shows you the Triassic, Jurassic rift basins, and these guys formed along normal faults. They were typical gray bands, and the red ones are where you can actually walk to them and study them, and they were freshwater lakes, and the sedimentary rocks in the lakes came from the Appalachian, so formed by the erosion of the Appalachian Mountains. Because of its active rift zone at the time, we have a lot of basalt volcanoes, which is very characteristic for rifting, if you remember. I hope you do. The name of the whole rift basin sequence is the Newark supergroup. Newark. You know, Newark next to New York. That's where all the European flights are flying out of, not the JFK. The basins are clearly freshwater basins, but they do contain a lot of evaporates because it has been dry from time to time. They have lots of very important fossils, a lot of dinosaurs, foot traces. You know, the dinosaur went to drink into these basins. And these sediments preserve the best climate cycle the Earth has, basically, because we have frequent volcanoes which give us really very good absolute age data, so we can really tell the duration of the cyclicity in these basins. We have a lot of basalt sills and basalt dikes. And one of the most famous basalt seal is the so-called Palisade seal, which is about 200 million years old, and it is along the Hudson River in New York, New Jersey. You probably have driven in that area. So let's talk a little bit about the cyclicity. So this is the sediment in the New York supergroup, the rift basins. They are very cyclic, as you can see right here. There are differences in colors and actually the sediment fabrics and the fossil preservation, and they are cyclic even in terms of their organic carbon content. They are shallow water, lacustrine or playa, which means dry lake bed, and then they have deeper water lake sediment. So you have the very shallow water, almost dried up lake, and then deep water lake basically. When it's a deep water phase, a lot of the times it has dark color, which means it wasn't really mixing, so it have had anoxic deep water in them, and so therefore they become laminated, microlaminated. Olsen have named each cycle, like the typical cycle, Van Houten cycle, and this actually records a complete lake cycle, which just means that from transgression to regression. So unconformity, transgression, regression, unconformity. That's one cycle. And so this here explaining the division one is the lake level rise, then the high stand is division 2, and the lake level fall, which means the regression, is division 3. So this is what's happening. This is one individual cycle, and then on top you have multiple of these individual cycle, and actually they packed into higher level cyclicity also. So that's what's really amazing. But this slide right here is just showing one lake level cycle. So the duration of one lake level cycle is about 20,000 years. And on this slide, this is one Van Houten cycles. And as you can see, 5 of those actually grouped into a 100,000 year cycle. And actually the Rift Basin also show a 400,000 year cycle also. So there's 20, 100,000 and 400,000 year cycles. So it's a hierarchy of different cyclicity, which is really interesting. Now, just something about the Rift Basins. They were graben or half graben. When you got a half graben, that just means you have one normal falls, and that makes the basin, and then it filled up. It's sediment. So that's how it looks like. It's very, very cyclic. And this slide just shows the typical dinosaur tracks. You also can find like fish and reptiles fossils or freshwater invertebrates like snail and clams and so on. This here is a typical picture of the very highly cyclic sediment in these rift basins. I guess I'm gonna stop right here and upload this segment, so I will see you in the next one.